Welcome to the Deep Dive, your shortcut to being truly well-informed. Today, we're diving deep into a scientific discovery that, well, it dramatically reshaped the entire 20th century. We're talking about something that influenced everything from global power dynamics right down to how we, generate electricity, nuclear fission. And at the heart of this world-changing breakthrough stands an extraordinary figure, the physicist Lise Meitner.
Absolutely. And Meitner's journey is it's not just remarkable for the science, which is brilliant, of course. It's a profound story of perseverance.
Right.
I mean, think about it. Groundbreaking theoretical work on nuclear fission, then escaping Nazi Germany as a Jewish woman, facing immense prejudice, and then taking this incredibly strong ethical stand against weaponizing her own discoveries.
Yeah.
Her life really embodies this idea of science with a conscience.
It really does. Our mission today is to unpack her extraordinary life for you. We'll look at the often challenging scientific and social context she navigated.
Yeah, the world she lived in.
Exactly, the specific moments of her breakthroughs, those aha moments, and the baffling reasons why her monumental contributions were, frankly, largely overlooked by some important groups.
A story in itself, that part.
Definitely. And ultimately, her enduring legacy as a scientist who, as her gravestone so beautifully puts it, never lost her humanity. So, let's get into it. Lise Meitner's story begins in Vienna, Austria. She was born back in 1878, the third of 8 children in a Jewish upper-class family.
And right from the get-go, she faced significant barriers. Barriers that, would be almost unimaginable today. Women at that time simply weren't allowed to pursue higher studies at public institutions in Austria. It wasn't possible.
So even showing talent early on.
Exactly. Despite showing exceptional early talent in math and physics, Meitner was first forced to train as a French teacher. That was the acceptable path.
Wow.
It wasn't until 1899, after undertaking 2 years of intense private study, just studying on her own, that she could even prepare for the university admission exams.
Incredible determination.
Absolutely. She finally earned her doctoral degree in physics from the University of Vienna in 1905, becoming only the second woman ever to do so. Her thesis, by the way, was on how heat flows through materials that aren't perfectly uniform inhomogeneous material. Pretty foundational concept for so much of physics.
So she gets her doctorate, a huge achievement in itself. But her scientific ambitions didn't stop there. That led her to make a pivotal move to Berlin in 1907, right? Eager to delve deeper into radioactivity.
Yes, Berlin was where the action was for radioactivity research. But what's truly remarkable, or maybe infuriating, is that even with a doctorate in physics from a top university, the gender prejudice was still just rampant in Berlin.
Still, even in Berlin.
Oh, yes. When she tried to attend Max Planck's lectures, Max Planck, the father of quantum theory, he reportedly greeted her kindly, but then asked, quite astonishingly, "You have a doctor's degree, what more do you want?"
Unbelievable.
And Emil Fischer, the director of the Chemistry Institute, where she wanted to work with Otto Hahn, initially forbade women from his main lab entirely.
Why? What was the reasoning?
He allegedly feared they'd set their hair on fire with Bunsen burners.
You cannot be serious.
I am completely serious. Imagine that logic.
That's just incredible. So a world-class physicist effectively banished to the basement.
Precisely. Meitner was famously confined to this small, former carpenter's workshop in the basement. She was forbidden from even going upstairs to talk to her collaborator, Otto Hahn, who was in the main lab.
So how do they even collaborate?
Well, he'd come down to her, or they'd meet elsewhere. And get this, she even had to use the toilet facilities at a nearby restaurant because women weren't allowed in the main institute building's facilities.
That is just degrading.
It's a stark illustration, isn't it, of how deeply ingrained these gender barriers were, forcing even brilliant minds like Meitner to take these circuitous and often demeaning paths just to do their work.
It's almost hard to fathom today the sheer tenacity required. A brilliant mind literally confined to a basement, working against a system that saw her gender as a liability. It makes her eventual breakthroughs all the more astonishing. So it was in that very basement workshop in 1907 that she began this really long collaboration, didn't she? Over 30 years with a young chemist named Otto Hahn.
That's right, at Humboldt University's radiochemistry laboratory. And their partnership was incredibly successful.
What made it work so well?
Their expertise was perfectly complementary. Meitner was the physicist, understanding the theoretical underpinnings, the radiation, the atomic processes. Hahn was the chemist, meticulous with experiments, identifying substances.
Ah, that interdisciplinary approach.
Absolutely key. And things did slowly improve. When women's education was finally officially regulated in Germany in 1909, Fischer, the director, finally relented, and she was at last allowed into the main chemistry department.
Okay, so out of the basement, finally.
Out of the basement. And this partnership led to some truly significant early achievements. For instance, in 1917, right in the middle of World War I,
Right.
they identified a brand new fundamental element, protactinium, element 91.
A whole new element. What was the significance of that?
It wasn't just filling a gap in the periodic table. It was a crucial piece in understanding the radioactive decay series of uranium, a huge step forward for the field, and it earned them the Leibniz medal.
And their collaboration continued to yield major discoveries after that too, right?
Oh, absolutely. In 1922, Meitner went on to discover the cause of something called the Auger effect. It's basically a unique fingerprint of electrons emitted from atomic surfaces when they get excited. It reveals a lot about their inner workings.
So she figured out why it happened.
Exactly. It was later independently discovered and, unfortunately for her credit at the time, named after Pierre Victor Auger. But she explained it first.
And her own career progressed despite the earlier hurdles.
Yes. Professionally, she was breaking barriers. By 1922, she became the first person appointed professor in theoretical physics in Germany, and then a full professor in physics in 1926. A huge deal for a woman at that time.
Just imagine that. In 1933, you've got the absolute pinnacle of physics gathering the Solvay conference in Brussels. Only 3 women were present out of 43 nuclear physicists. And Lise Meitner was one of them, alongside Marie Curie and Irene Joliot-Curie.
It really underscores just how singular her talent was and how much she had overcome to be in that room. And this is the backdrop, this rapidly evolving scientific landscape that really set the stage for their later, most groundbreaking work. The early 20th century was just an explosion of discovery in physics.
Right, laying the groundwork.
Exactly. You had Wilhelm Röntgen discovering X-rays in 1895, Henri Becquerel finding spontaneous radioactivity in 96, J.J. Thomson discovering the electron in 97.
Okay.
Then Max Planck formulated his quantum law of radiation in 1900. Ernest Rutherford and Frederick Soddy showed elements could actually disintegrate, change into other elements in 1902.
A radical idea, then.
Absolutely. And crucially, Albert Einstein formulated special relativity and his famous EMC equation in 1905. And then James Chadwick discovered the neutron in 1932. That was particularly important.
The neutron, why was that so key?
Because the neutron, being neutral, could penetrate the atomic nucleus without being repelled by the positive charge. It became the perfect tool to probe the nucleus, which led directly to the work on fission. All these discoveries built the foundation Meitner and Hahn were working on, leading them right to the edge of something incredible.
However, this period of incredible scientific advancement coincided with something truly terrible. The ominous backdrop of the 1930s, the terrifying rise of Nazism. And this would dramatically impact Meitner's life and her work in the most profound way.
Indeed. It's a dark turn in the story. Despite having converted to Lutheranism way back in 1908, Meitner was considered Jewish under the Nazi racial laws.
Her conversion didn't matter to them.
It's not at all. Her Austrian citizenship initially provided some protection, but her situation became desperate after Germany annexed Austria in the Anschluss of March 1938. Suddenly, she was stateless, German law applied, and she was incredibly vulnerable.
So the protections vanished overnight.
Overnight, the prejudice escalated rapidly. She was dismissed from her position at the University of Berlin, barred from attending scientific meetings, her contributions deliberately minimized. Her colleague, Kurt Hess, an ardent Nazi, even stated chillingly that the Jewess endangers this institute.
That's horrifying.
And perhaps the most heartbreaking part. Her longtime collaborator, Otto Hahn, the man she'd worked with for 30 years, eventually told her she must leave the institute. She recorded it bitterly in her diary, saying he had, in essence, thrown me out.
Wow, after all that time together.
Yeah, it's complex, Hahn's role, but for her, it felt like a profound betrayal on top of the existential threat.
Her escape then, in July 1938, it sounds like something out of a movie. It was incredibly risky, wasn't it?
Oh, absolutely. High-stakes thriller is right. Imagine this. Lise Meitner, this world-renowned physicist, forced to flee Germany, essentially disguised as a tourist. She had help from Dutch physicists Dirk Koster and Adrian Fokker.
Right.
She traveled with just 2 small suitcases and only 10 marks in her purse. She was terrified of the border guards, obviously.
I can only imagine the fear.
The tension at the Dutch border, she recounted it later, must have been unbearable when a Nazi patrol came through checking documents. Her Austrian passport was completely outdated by then because of the Anschluss.
So it was basically worthless.
Technically, yes.
Yeah.
But somehow, whether through luck or the guards' ignorance, they just handed it back without question. Her relief must have been overwhelming.
A life-or-death moment, literally hanging on an outdated passport.
Truly a nail-biting moment. And once she was safely across the border in the Netherlands, Dirk Koster sent a coded telegram back to Hahn in Berlin to confirm she was safe.
What did it say?
The message simply read, "The baby had arrived." A quiet confirmation for such a dramatic, dangerous escape.
So Meitner gets out. She arrives in Sweden in September 1938. But it wasn't exactly smooth sailing there either, was it? New challenges arose.
Not at all. She found herself a stateless refugee at Manne Siegbahns Nobel Institute in Stockholm. Siegbahn was a prominent physicist, but, well, the conditions weren't ideal. She sorely lacked not just instruments and resources, but perhaps even more critically for a top scientist, that vital professional dialogue, the back and forth with colleagues. Siegbahns Institute wasn't really focused on nuclear physics in the same way her Berlin group had been.
So she was isolated again in a different way.
In a different way, yes. And this was particularly difficult because she'd been working on this really critical project back in Berlin, inspired by Enrico Fermi's 1934 experiments.
What was Fermi doing?
Fermi was irradiating elements with slow neutrons. These neutrons, because they move slowly, have a better chance of being captured by an atomic nucleus, potentially creating new, heavier elements or isotopes. It was cutting-edge stuff.
And Meitner was working on that when she had to flee?
Exactly. That project got suspended when she fled Germany. Though she tried to stay involved from afar, corresponding with Hahn, even meeting him secretly in Copenhagen with Niels Bohr to discuss the ongoing research.
Right. And then comes this pivotal moment in December 1938. She gets a letter from Hahn.
Yes, just as she was preparing for a Christmas holiday in a small town called Kungälv near Gothenburg in Sweden. She received a letter from Otto Hahn summarizing these truly baffling experimental results they'd gotten back in Berlin.
Baffling how?
When they irradiated uranium, the heaviest natural element, with neutrons, they expected maybe slightly heavier elements. Instead, they found barium.
Barium, but that's much, much lighter than uranium.
Exactly. It's about half the mass.
Yeah.
Chemically, there was no doubt it was barium. Hahn and his colleague Fritz Strassmann were sure of that. But physically, how could irradiating uranium produce barium? It made no sense based on existing nuclear physics. Hahn wrote to Meitner asking, basically, can you, the physicist, explain this?
And this is where the legendary aha moment happened, isn't it? The kind of scientific breakthrough you read about, but it actually happened during a Christmas walk in the snow.
That's the story, yes. She recounted it vividly. She was walking in Kungälv with her nephew, Otto Robert Frisch, who was also a nuclear physicist and had also fled Germany earlier in 1933. He'd come to visit her for Christmas.
So aunt and nephew, both physicists, puzzling over this bizarre result.
Exactly. Their conversation focused entirely on Hahn's inexplicable results. They started thinking about Niels Bohr's recent model of the atomic nucleus, which pictured it behaving sort of like a liquid drop.
A liquid drop. How does that help?
Well, a liquid drop, if it gets disturbed enough, can wobble, elongate, and maybe even split into two smaller drops. That was the analogy.
Okay.
And during that walk, the pieces just clicked into place for Lise Meitner. She realized the uranium nucleus wasn't just chipping off a small piece, as everyone assumed in nuclear reactions back then. It was actually splitting in half.
Splitting the atom.
Essentially, yes. And she quickly did the calculations right there, possibly leaning against a tree, using Einstein's Epitaxis. She figured out that the two smaller nuclei flying apart, due to their positive charges repelling each other, would release an enormous amount of energy. Around 200 million electron volts per split atom.
200 MeV. That's huge on an atomic scale.
Absolutely enormous. For a single atomic event, it dwarfs chemical energy releases. Frisch then immediately thought of a name for this new process. He proposed fission, borrowing the term from biology where it describes cell division.
Fission, and that was it, the explanation.
That was the physical explanation for Hahn and Strassmann's chemical findings. It was revolutionary.
The publication sequence of this discovery is important to note, too, especially given what happened later with the Nobel Prize. How did that play out?
All right, this is crucial. Hahn and Fritz Strassmann published their chemical findings, the discovery of barium first, in the German journal Die Naturwissenschaften on January 6, 1939. They were hesitant to include the physics explanation they'd just gotten from Meitner, partly perhaps because of the political situation, acknowledging a Jewish woman in exile. Meitner and Frisch then quickly wrote up their paper, providing the crucial physical explanation, the fission concept, and the energy release calculation. They sent it to the prestigious British journal Nature. It appeared on February 11, 1939, so a bit later, delayed partly by editorial back and forth.
So the chemistry came out slightly before the physics explanation?
Correct. And Frisch, being an experimentalist too, immediately went back to Copenhagen after that Christmas visit and designed an experiment to actually detect the high-energy fragments flying apart from fission. He got results within days, measuring the huge kinetic energy of the products. This was the first direct experimental confirmation of fission and the first clear demonstration of Einstein's EMC4 in action in this context, mass being converted into that tremendous energy. His experimental paper appeared in Nature shortly after the theoretical one.
So theory and experiment confirming each other rapidly. What was the reaction from the wider physics community?
Niels Bohr's reaction upon hearing Meitner and Frisch's explanation before he left for a conference in the U.S. perfectly captured the moment. He apparently slapped his forehead and exclaimed, "Oh, what fools we have been. We ought to have seen that before."
Wow.
He immediately understood the implications. Bohr then carried the news to the United States, and it spread like wildfire. Within weeks, laboratories across the world had replicated the experiments and confirmed fission. The nuclear age had, without a doubt, truly begun.
The discovery of nuclear fission, as you said, spread like wildfire. It had this immediate electrifying effect on the scientific community, but also the potential for a chain reaction leading to enormous explosive power became terrifyingly clear to everyone almost instantly, didn't it?
Indeed, the physics was clear. If each fission released neutrons, and those neutrons could cause more fissions, you could get an uncontrolled chain reaction. Release that energy all at once, and you have a bomb of unimaginable power.
And this was happening just as World War II was looming.
Exactly. This terrifying knowledge, if weaponized, presented an unthinkable threat. The specific concern was that Nazi Germany, where fission was discovered chemically, might be the first to develop such a weapon. This fear is what prompted figures like Leo Szilard and even Albert Einstein, who was a pacifist himself, to write that famous letter urging President Franklin D. Roosevelt to start a U.S. program.
Which eventually became the Manhattan Project.
Correct, the race was on.
Yet, Lise Meitner, whose insight was so crucial to this discovery, held a very different, resolute moral stance on using it for a weapon, didn't she? Her pacifism seems deeply rooted.
Absolutely. It wasn't just an abstract principle for her. It was shaped by her direct, harrowing experience as a volunteer X-ray nurse during World War I. She'd seen the horrors of war firsthand, including the devastating effects of chemical weapons like nerve gas.
So when the call came for the Manhattan Project,
She refused point blank. She was actually invited to join the British mission going to Los Alamos. But her response was unequivocal. I will have nothing to do with a bomb.
just a flat refusal.
A flat, principled refusal. She also consistently rejected offers from movie studios wanting to dramatize her story, especially her escape and the mother of the bomb angle. She called one script nonsense from the first word to the last and stated flatly it was against my innermost convictions to be shown in a film. She even gave friends power of attorney to sue if her name was used without her permission in such a context.
That's incredible control over her own narrative, or trying to maintain it.
Yes, she fiercely guarded her integrity and didn't want her work associated solely with destruction.
How did she react then when the news came of the atomic bombings of Hiroshima and Nagasaki in August 1945?
She was profoundly shocked and distressed. Reports say she went on a 5-hour walk just to try and process the news. It must have been devastating to see the ultimate outcome of the physics she helped uncover used in that way.
Yet the press often painted a different picture, didn't they?
Oh, completely. The American press, in particular, often sensationalized her role after the war, dubbing her the Jewish mother of the bomb or the woman who escaped with the secret of the bomb, titles she absolutely deplored. She did gain some fame, though, even giving the first transatlantic radio interview with Mrs. Eleanor Roosevelt.
Wow. And her feelings towards her former colleagues in Germany, especially after the war.
She was bitterly critical and quite outspoken about it in private letters, particularly towards scientists like Otto Hahn and Werner Heisenberg. She felt they and many others had been complicit through their passive resistance or outright collaboration with the Nazi regime.
Did she confront Hahn directly about this?
Yes, in a famous, very raw letter she wrote to him in 1945, but didn't send until 1946. She wrote, "You all worked for Nazi Germany, and you tried to offer only passive resistance. Millions of innocent human beings were allowed to be murdered without any kind of protest being uttered." She felt they had prioritized their careers and institutions over moral courage.
Powerful words.
Very. and it shows her deep sense of justice and morality, even amidst the complexities of wartime loyalties and pressures.
And through all this turmoil, the prejudice, the escape, the war, the bomb, she maintained this profound belief in the purpose of science itself, didn't she?
She really did. She had this almost spiritual view of the scientific endeavor. She once stated, "Science makes people reach selflessly for truth and objectivity. It teaches people to accept reality with wonder and admiration, not to mention the deep joy and awe that the natural order of things brings to the true scientist."
That's a beautiful sentiment, a powerful reminder of what science at its best can be. It feels so vital today. Okay, let's talk about the Nobel Prize. Despite her undeniable, absolutely crucial contributions to understanding fission, there was this glaring omission in her career that still sparks debate today. The 1944 Nobel Prize in Chemistry was awarded solely to Otto Hahn for his discovery of the fission of heavy atomic cores. What happened there? How could Meitner be left out?
It's one of the most discussed and frankly criticized decisions in Nobel history. The evidence of the injustice, as you look back, is pretty extensive and yet infuriating.
She was nominated, though, right? People knew her role.
Nominated. She was nominated a remarkable 48 times for the Nobel Prize between 1924 and 1965, 29 times in physics, 19 times in chemistry, often jointly with Hahn or with Hahn and Strassmann or with her nephew Frisch. And these nominations came from top physicists like Max Planck, Niels Bohr, James Franck. The giants of the field knew her significance.
48 times. So the scientific community clearly recognized her contribution. Why the exclusion by the committee? What was their reasoning?
Well, looking at the Nobel Committee protocols, which are now public for that era, the discussion seems to have hinged narrowly on the publication dates. Hahn published the chemical discovery first. They largely ignored the flood of calls from international physicists, emphasizing that Meitner provided the essential physical explanation that made sense of Hahn's data.
That seems like a very narrow interpretation.
Extremely narrow. Some committee members, like Theodor Svedberg, cited difficulty in determining the initial significance of uranium research, which, frankly, seems like a weak excuse given the earth-shattering impact fission had almost immediately. And then there was Måns Zelmerlöw, the influential Swedish physicist at whose institute Meitner worked in exile. He was on the committee and seems to have been instrumental in the decision that only Hahn should be recognized.
Zelmerlöw, why would he argue against her?
The reasons are debated, but publicly released Nobel archive documents suggest a combination of factors. Definite flaws in the Nobel decision-making process, certainly a lack of scientific expertise in theoretical physics. On the chemistry committee evaluating an interdisciplinary discovery, and perhaps most damningly, many historians believe her exclusion was a rare instance in which personal negative opinions apparently led to the exclusion of a deserving scientist.
Personal opinions. Like prejudice.
It seems likely. This might have stemmed partly from Siegmund's alleged royal Swedish jealousy, perhaps resentment towards this brilliant refugee physicist working in his sphere, and almost certainly ingrained prejudices related to her being a Jewish woman and a refugee at that. It's a truly, truly unfortunate chapter in the Nobel story.
It certainly is. Especially poignant given that Otto Hahn himself, in his 1946 Nobel lecture, did give full honor to Meitner and her contributions. It speaks volumes that he acknowledged her role publicly, even if the committee didn't officially.
Yes, he did acknowledge her fundamental contribution in his lecture, which was important.
But while the Nobel Prize unjustly eluded her, the recognition she did receive later in life certainly affirmed her status as one of the century's great scientists, didn't it? Things did get better for her.
Her circumstances in Sweden did improve significantly after the war, thankfully. The Prime Minister himself, Tage Erlander, intervened in 1947. He arranged a proper professorship and a laboratory for her at the Royal Institute of Technology, KTH, in Stockholm. This allowed her to finally leave Siegmund's less-than-supportive institute.
Ah, so she got a better working environment.
A much better one, yes. She became a Swedish citizen in 1949, though she also retained her Austrian citizenship. She even advised on the construction of Sweden's first nuclear reactor, R1, which was built subterraneanly under KTH.
And the awards started coming.
Yes, the accolades were numerous and prestigious. He was named Woman of the Year by the National Women's Press Club in the USA in 1946, which brought her considerable public attention there. She received the Max Planck Medal from the German Physical Society in 1949, a huge honor from her former colleagues. And significantly, in 1966, she shared the prestigious Enrico Fermi Award, a major American prize, with Otto Hahn and Fritz Strassmann. This was seen by many as a partial correction of the Nobel injustice. She was also appointed a foreign member of the Royal Society in London in 1955, a very high scientific honor.
And the ultimate honor perhaps came posthumously.
Indeed. In 1997, element 109 on the periodic table was officially named Meitnerium, MCHO, in her honor. A truly fitting tribute, cementing her name in the fundamental building blocks of the universe she helped understand. She's also the only woman to have a statue dedicated solely to her outside Humboldt University in Berlin, erected in 2014. These recognitions, though some came late, really speak to her lasting impact.
Speaking of her time in Stockholm and lasting impact, it's worth mentioning another key figure in her life there, Oscar Klein, another physicist who was also a refugee.
Yes, Oscar Klein was very important for her, especially intellectually. He was actually 16 years older than Meitner, but he became one of her closest connections to the cutting edge of modern theoretical physics, helping her keep up with developments while she was somewhat isolated at Siegbann's Institute initially.
And Klein was a significant physicist himself.
Oh, absolutely. Klein made major contributions to quantum field theory, cosmology. The Kaluza-Klein theory is named partly after him. And like Meitner, he was Jewish and had found refuge in Sweden. He was also very active in helping other Jewish refugee scientists like Walter Gordon find safety in positions. So they shared that common, difficult experience too.
It's fascinating how these networks of refugee scientists supported each other. Okay, let's zoom out for a moment. Meitner's work unlocked the immense power hidden within uranium right here on Earth. But her discovery also invites us to look up, far beyond our planet, and ask a truly cosmic question. Where does an element as heavy and potent as uranium even come from in the first place? How is it made in the universe?
That's a fantastic question, and it connects her work to the deepest mysteries of cosmic origins. Modern astrophysics and nuclear physics have given us a pretty good picture, actually. It happens in stages.
Okay.
The very lightest elements, basically hydrogen and helium and a tiny bit of lithium, were almost exclusively formed in the first few minutes after the Big Bang itself, about 13.8 billion years ago. That's primordial nucleosynthesis.
The leftovers from the universe's birth?
Exactly. But everything heavier than that had to be made later. Elements like carbon, nitrogen, oxygen, the stuff we're mostly made of, are forged in the incredibly hot, dense cores of stars through nuclear fusion. Our own sun is doing this right now, fusing hydrogen into helium. Larger stars fuse heavier elements, up to iron.
So stars are element factories. What about the really heavy stuff like gold, lead, and uranium? Iron is kind of the limit for normal stellar fusion, right?
Precisely. Fusing elements heavier than iron actually consumes energy rather than releasing it, so stars can't build them that way. For the very heaviest elements, including uranium, the latest scientific understanding points to an even more dramatic, violent origin. They're thought to be created primarily during the cataclysmic merging of neutron stars.
Merging neutron stars. There's incredibly dense remnants of massive stars.
The very same. When two neutron stars spiral into each other and collide, the conditions are unbelievably extreme, immense temperatures, pressures, and crucially, a flood of free neutrons. This allows for a process called rapid neutron capture, or the R process.
The R process.
Yeah. Existing heavy nuclei rapidly soak up lots and lots of neutrons before they have time to decay, building up to the heaviest elements like uranium, plutonium, gold, platinum. Then, subsequent radioactive decays shape the final abundance we see.
And we have evidence for this.
We do now. A huge confirmation came in 2017 with the detection of gravitational waves from a neutron star merger, an event called GW1708 Stone. Telescopes quickly looked at the location and saw the electromagnetic glow, the kilonova, following the merger. And the light spectrum from that kilonova contained the telltale signatures of freshly synthesized heavy elements, confirming that these mergers are indeed major cosmic factories for things like gold and uranium.
Wow. So Meitner's foundational work, which unlocked the power of uranium here on Earth, ultimately connects us to these incredibly violent, spectacular collisions of dead stars, perhaps billions of light years away. What an incredible scope her discovery encompasses.
It really does put it in perspective, doesn't it? The atoms she studied were forged in cosmic cataclysms. She eventually spent her peaceful retirement years in Cambridge, England, living near her nephew Otto Frisch and his family. She passed away peacefully in her sleep in 1968, just shy of her 90th birthday. She's buried near her brother Walter in a small village churchyard in Bramley, Hampshire.
And as we mentioned at the start, the inscription chosen by Otto Robert Frisch for her gravestone, it just perfectly encapsulates her spirit, doesn't it? Lise Meitner, a physicist who never lost her humanity.
It's incredibly powerful. And her legacy truly endures, not just in the reactors and, sadly, the weapons that followed her discovery, but perhaps more importantly, in her quiet, dignified fight against prejudice and her unwavering ethical stance.
Did she ever speak out more publicly about the sexism she faced later in life?
She did, though typically with characteristic understatement. In a 1959 lecture in Vienna titled The Status of Women in the Professions, she finally addressed some of it directly. She spoke about the discouraging and sometimes comical prejudices she encountered throughout her career. And she noted, even in 1959, that while progress had been made, not all that can be desired has been achieved. In principle, nearly all male professions have become accessible to women. In practice, things often look different.
A statement that still resonates powerfully today, doesn't it?
It certainly does. Even with more recent progress, like Donna Strickland sharing the Nobel Prize in Physics in 2018, only the third woman ever to win it in physics after Marie Curie and Maria Gopper-Mayer. Meitner's words remind us that the path isn't always easy, and systemic issues can persist long after legal barriers fall.
So bringing it all together, Lise Meitner's story is just this incredible tapestry of unparalleled scientific brilliance, sheer perseverance against immense prejudice, both sexism and anti-Semitism, and an unwavering moral compass that really set her apart, especially in a world grappling with the terrifying implications of her own discovery.
Absolutely. And that leaves us perhaps with a final provocative thought for you, our listener, to consider. How do we, as individuals and as a society, ensure that scientific progress, with all its power, is always guided by a deep commitment to human values? What did Meitner mean by a humanity that should never be lost? And how do we uphold that today, especially when faced with the most profound and challenging knowledge that science continues to uncover?
Yes.
Something to think about.